Hey guys, here we are. Homework 4. So we're looking at the first question here, T6.4. It says, suppose a student is randomly selected from your school. Which of the following pairs of random variables are most likely independent? So what they're really asking was, would knowing one help you predict the other? So let's think about this. Would knowing the student's height help you predict their weight? Well, yeah, maybe it's not a perfect predictor, but if somebody's less than 5 foot, they probably weigh less than 120 or 130 pounds. If someone's 6'5", then they probably weigh well over 200 pounds. So notice knowing someone's height does help you predict their weight. What about your IQ and your GPA? So if someone has a high IQ, maybe it's not a perfect predictor, but it would help you. Or if someone has a low IQ, they're more likely to have a low GPA. What else? Your PSAT score and your verbal score. So most of my students get a pretty close score. Kids that Christmas treed the PSAT probably Christmas treed both the math score and the verbal. So if you had a low math score, probably had a low verbal. Not always, but one would help me predict the other. So again, it's not like all of these are true. It's which one would be the most likely. So average amount of homework and your grades, your GPA. Lastly, the amount of homework you do per night and your height. So, short people do their homework, tall people do their homework. There's no real correlation there. So that's why we picked E. What's next? Okay, so let's take a look at 6.5. It says a certain vending machine offers 20 ounces a bottle of soda for $1.50. The number of bottles bought from the machine on any day would be 50 with a standard deviation of 15. So you can kind of see this graph I made. On average, we sell 50 cans of soda from the machine plus or minus 15. So this graph shows us the distribution of bottles sold. Now, it says let Y be. So letting another variable, we can still use this data to create that data. Let Y be equal to the total revenue. So if I sold 50 cans from the machine, X, Y would just be 50 times $1.50. So I should predict on average to make about $75 a day. And this graph should look like that graph. So what about the standard deviation? Well, we can use these same numbers. So 65, if I sold 65 cans for $1.50, I should expect to make $97.50. So this would help me work backwards to figure out what would be the standard deviation of this graph. And standard deviation is just the distance between one standard deviation to the left or one standard deviation to the right. So off to the side, you can see I took 97.5 minus 75, and I got 22.5. That's why I picked the standard deviation of 22.5. Another way to think about this is, like I said, just merely multiplying. So if you sold 65, you're predicting to make 97.5. If you sold 50, you're predicting to make 75. We know that that 65 is one standard deviation to the right of the mean. How else could you have done it? You could have taken the standard deviation of 15. So just taken the raw number of 15 and multiplied. So we know that when we add and subtract, the standard deviation doesn't change. But when we multiply, the standard deviation does change. So 15 times 1.5 is 22.5. Okay? Next, let's look at this question. It says AP 1.9. Before he goes to bed, Mr. Clean pours dishwasher powder on his dishwasher and turns it on. Each morning, his wife weighs the box of dishwash powder. From an examination of this data, she's saying it is rather consistent. He uses the same amount of powder each night. Which of the following must be true? So if he uses the same amount of powder each night, that sounds like a linear relationship where the amount he uses each night is merely the slope. So now we just have to look at how they may change or ask this question in two different ways. So first, if they said the number of days that went by. So after the first day, maybe he used 10 ounces of the solution. And on the second day, he's used 20. And by the third day, he's used 30. And by the fourth day, he's used 40. You get the point. It sounds like a linear, because each day, it says, each night, he uses about the same amount. Now, they could also ask, instead of graphing how much he uses each day, how much is left after each day? And so that would look differently. So after the first day, if the box had 40 in it and you used 10, then you'd be down, you're left with 30. And after the second day, you're left with 20. And the third day, you're left with 10. And you see the point. If they ask how much is left over, my graph goes down. If they've asked how much you've used so far, the graph goes up. Now let's look at our choices here and try to make sense of these. There's a high positive correlation between number of days passed and amount left in the box. So that's a false. That it actually should be a negative correlation. A scatter plot with days since purchase and the total amount of dishwasher used as a response variable would be strong positive. So that would be true, because that would be the amount days passed and amount used. That's positive. Let's look at 3. The correlation between the amount left and the amount used should be very close to -1. Now, that would be a third graph. So, if the old thing had 40 ounces in it, if I use 10, amount left would be 30. If I use another 10, amount left is 20. If I use 30 total, or another 10, amount left is only 10 left. So notice this would be very close to -1, meaning a negative correlation. Sorry, my light likes to turn off. A negative correlation that's almost perfectly negative, should be negative, and it's going down because the more I use, the fewer that is left in the box. Okay? Let's press on. So we see here on question AP 1.6, if this is normal, which of the following gives the best estimate for the mean and the standard deviation? So we know the mean is somewhere in the middle, so we've eliminated A and B. And we know the standard deviation, if it's normal, then it should abide by the 68, 95, 99.7 rule. So what does that mean? Well, it means all the data, 68 is between one standard deviation to the left and right, 95% of the data is within 2 standard deviations to the left and right, and nearly all the data, 99.7% of the data, so somewhere between here and here. So I could read this off and write, okay, so each of these tick marks is 25, so 425 minus 25, so it looks like the width of almost all the data is 400. And to find one standard deviation, you're looking for just this distance right here, the distance between the mean and one standard deviation to the right. So we have to divide this in 6 because there's 3 standard deviations to the left and 3 standard deviations to the right. So when we take 400 divided by 6, we get 66. So that's not exactly, but this is the closest answer I have. So what does that mean? If 3 standard deviations to the right look about 2 hops, right? And 3 to the left look about 2 hops. So this is our best approximation of the standard deviation, even though this number is not exactly that number because it is an approximation. All right, last question. If you're planning an experiment to determine the effects of gasoline and the weight of a car, so you're really interested on the effects of these gasolines. So let's say the gas comes from Amoco, Marathon, and Speedway. The only way to know if Amoco is better than Marathon or is better than Speedway, you need, when you do your test, each of these to have an equal chance of being chosen. So we know that equipment wears down over time. And so if just by chance Amoco gets picked first, and if we later find out it's really whatever brand that got picked first ends up being best because the car's not worn down already or the engine parts are not warmed up. In order to actually be able to say that it is in fact the brand of gasoline, we need to make sure that each brand of gasoline has an equal chance of being chosen and has an equal chance of either being first, second, or last. Okay? Also, they want to know if the weight that we add a car has any effect on that as well. So again, for the same purpose, we want each of our tests to have an equal chance of being light, medium, or heavy. So our only choice here is, since there would be 9 combinations of these, we want to make sure that we run the car several times and make certain that all 9 possible combinations have an equal chance of being chosen in a very specific random order. All right, so each combo needs an equal chance of being chosen and an equal chance of occurring first, middle, or last. Okay? Thanks for joining us, guys. See you next time.